Question 5, and we're on to the work energy principle. Now, to begin with, we've got a nice simple question where we're just looking at finding the potential energy lost. So we know that's going to be gravitational potential energy, which is calculated by mg change in height. In this case, the mass is 2, and the change in height is going to be the drop from A down to B. And that drop is going to be measured as 5 sine 30, which gives me 49 joules of energy. The next part of this question, we're talking about speed and we're talking about the work energy principle. So we're now going to use the work energy principle to find this friction force that we've been acting against. What does the work energy principle say? Well, if I have an amount of potential energy that has been lost, we know that that must all go to kinetic energy and work done. So the total amount of energy that I have put into the system is going to be 49 joules. The kinetic energy is going to be calculated as a half times by mass times by the velocity at b squared, which is 4 squared, plus work done. Now work done is force multiplied by distance, and as the particle travels from A to B, it's travelled a distance of 5 meters. So that's to say that 49 is equal to 16 plus 5f. So subtracting, I've got 33 is equal to 5f. So 6.6 is going to be the force, the frictional force, in fact, acting against this particle. We now want to continue and find the coefficient of friction. In order to do that, let's just set ourselves up one of our little diagrams. Think about this particle that's going to be moving down the plane. It's got 2g acting downwards. It's got the friction force F max acting upwards. Let's also resolve for the parallel component to friction, which is going to be 2g sine 30, as the angle in the top here is going to be the same as the angle that we had at the bottom here. I also need to know that my reaction force here, R, is going to be equal to part of the weight that's acting perpendicular to the plane, which is 2g cosine 30. Now I can move on and say that R must be equal to 2g cosine 30, and we can start to think about the friction force F max, which we know will be equal to mu multiplied by R. We also know that the maximum friction force we have already found. This was our 6.6 from earlier, which is going to be mu multiplied by R, which is 2g cos 30. So my mu value is going to be 6.6 divided by 2g cos 30, which works out to be 0.389. Finally, I'm going to think about particle P projected down the plane with a speed of 3 meters per second. We're going to think that friction remains constant, and we want to find the speed as it reaches B. So let's go back to our work energy principle. We're still putting the same amount of potential energy into the system. This time we're not just looking at a gain in kinetic energy, we're looking at a change in kinetic energy. So I'm just going to write that as delta Ke. And I'm still going to have to consider work done. The potential energy we had was 49 joules. The change in kinetic energy is going to be a half m, which we know here to be 2. So let's change that to a half multiplied by 2. Lots of v squared, what we're interested in, the final velocity of the particle, minus the initial velocity squared, plus the work done. And the work done was 6.6 multiplied by 5. So that's to say that 49 is equal to v squared minus 9 plus 33, or to say that 25 is equal to v squared, which tells us that v must be 5.